My name is Sailesh Krishnamurthy. I work at Amazon Web Services. I'm an engineering manager for the Amazon Aurora database team. I'm here to talk today about Aurora. I'll do a deep dive into how we build the system and talk about some of the new things that we've added to the system. So the agenda for the talk, first part would be catching up. It's now about a little over 18 months since Aurora went GA. So we'll talk a little bit about, again, just a refresher on Aurora, who's using it. Then I'll dive into two separate sections. One, I'll focus on performance, and the other will be about availability. So let's start with Aurora. Amazon Aurora tries to reinvent and reimagine databases for the cloud. At a high level, it's about the speed and availability of high-end commercial databases with the simplicity and cost profile of open source databases. It has drop-in compatibility with MySQL and, as we recently announced, Postgres as well, with very simple pay-as-you-go pricing. Now, all of this is delivered as a managed service. So those of you who have used AWS before might be familiar with RDS, Relational Database Services. And Aurora is delivered as an engine under the umbrella of the RDS managed service. So there are three pillars of what I like to talk about when we reimagine the database for the cloud. The first is a scale-out distributed multi-tenant design point. The second is about a service-oriented architecture. Today people talk a lot about microservices versus monolithic implementations. Mostly they talk about it in the application layer, but we are heavily leveraging this idea of independent services that can be managed and deployed separately. And in our case, not just is Aurora implemented using multiple internal services, Aurora actually relies on other AWS services as well. So I'll talk about some of that. And finally, a big part of a managed service is that it's fully managed and we can automate a lot of the painful administrative tasks. So let's start with the first big pillar, if you will, a scale-out distributed multi-tenant architecture. So normally, if you think about a database engine, you would have a SQL execution layer, a transactions system, a buffer cache, and a logging and storage component. Aurora took the logging and storage component and built it out as a separate scale-out service, which is log structured and optimized for OLTP database workloads. So if you think about a database volume, a storage volume, the storage volume is striped across hundreds of storage nodes that are distributed in 3 availability zones, or 3 AZs. And you can think of an AZ as at least a data center. An AZ is separated by another AZ by about 5 to 15 miles. So each copy of your data is replicated, each page of your data is replicated into 6 copies, with 2 of them in each availability zone. And the most important thing to remember when you think about Aurora is really in the API between the storage service and the database engine. Normally, a database engine talks to some kind of, if it's talking to some network attached storage, is operating on a model where you read and write blocks. In Aurora, you read blocks, read pages, just as you would in a normal database engine. But on the write path, it is very different. And instead of writing full pages, you write redo log records, or deltas. And so that's where the log structured aspect comes in. It's not just in the API between the database engine and storage, but it's in how these logs are organized with the various different data pages that are managed by the storage service. So if you can think about offloading 1/4 of the database engine and making it available as an independent scale-out service. And we have plans to take the same principle and apply it to various other pieces in the database engine. And over time, we'll be able to split more aspects of the database engine into the scale-out service. So that's the first pillar of a reimagined database service for the cloud. The second piece, in terms of leveraging the cloud ecosystem, in past presentations, we've talked a lot about the underpinnings of how Aurora is built, how we use S3 and DynamoDB and the simple workflow service. But one of the new things that we've been doing over the last 6 to 9 months is to actually leverage the wider AWS cloud ecosystem and make it a central part of the Aurora service itself. So the very first aspect of this is with Lambda. I'm not sure how many of you are familiar with Lambda, but AWS Lambda is a mechanism for serverless computing where you can upload pieces of code, associate them with HTTP endpoints. And one of the things we now offer in Aurora is from your MySQL or from your Aurora MySQL stored procedures and triggers, you can actually invoke Lambda events. So that's a way to kind of break out of the box of the database engine. We have, for instance, customers who use a commercial database engine with a native inbuilt queuing system. And instead of building a queuing system inside the database, they can use Lambda to send messages to something called SQS, a simple queuing service that's offered by AWS. So that's an example of integrating with the rest of the cloud ecosystem. The next aspect is S3. We see in AWS customers, S3 plays a central role. People use S3 as a hub, as a data hub. They keep data there. Maybe it's data from Redshift, maybe it's data from some other queuing system. And so a lot of times data comes in to the database from S3. And now we made it easy to load data from S3. We also store snapshots and backups in S3. This is something that we do under the covers. And one of the things we are releasing shortly is to be able to take the results of queries and store them in S3. So in MySQL you can say select into out file. Soon you'll be able to say select into out file S3, and you'll be able to declare an S3 bucket and have the results of queries get stored there directly. Third aspect is around security and authentication. IAM is AWS service for identity access. And so now with Aurora, you can use IAM roles to manage who gets to connect to a database, how they get to connect, and how they get to authenticate with the database. So that's something that we've also released. And finally, we are putting in the infrastructure to upload various systems metrics and logs to CloudWatch. We announced auditing support for Aurora, and right now these audit logs have to be downloaded. But one of the things that we are putting in is the mechanism to seamlessly auto-upload them to CloudWatch. So these are various ways in which we are leveraging the cloud ecosystem. We plan to do more of these in the future. But it's a big part of how we think of the database as not just as a sink of data, but as something that participates in the wider ecosystem. The third aspect, automating administrative tasks. What we'd like, our vision is that people like you focus on thinking about how to use the database, schema design, and even some aspects of optimization, optimizing queries and thinking about your strategies for schema evolution, writing queries, thinking about how all of that works into your application model. And what we would like to offer is all of the items here, managing failover when you have faults, dealing with backup and recovery, dealing with security, providing industry standard compliance practices, to be able to scale easily, to apply maintenance windows and to patch the database engine as necessary, and to provide monitoring and to be able to figure out how the system is actually operating. So our real vision is that we can take care of the things that don't add value to you directly and let you guys focus on applications and your business. Aurora is the fastest growing service in AWS history. It's used by over 60% of the top 100 AWS customers. It's used in a very large number of gaming customers. It's a bunch of different logos in the slide. These are all people who are using Aurora. It's just a sample. It's, like I said, it's growing really fast. I'd classify the people who are moving to Aurora in two buckets. There's one big bucket of people who come in from MySQL engines, people who are using MySQL, MariaDB, and these could be either people who are running in a self-managed fashion, either on EC2 or self-managed on-premise, or they might be using already RDS, using RDS MySQL. And the reasons they come in typically are one about performance. Your mileage may vary, but we've seen up to 5x performance improvement by coming to Aurora in terms of throughput. Better availability and durability, faster recovery, being able to restore snapshots fast. These are all big parts of the value proposition of Aurora. Reduce costs, although we charge more for RDS Aurora than RDS MySQL. People who are able to consolidate databases often see a reduction in their bills. And we've seen quite often people saving up to 60% of their RDS MySQL bill by coming to RDS Aurora. And finally, if you're already on a MySQL engine, it's relatively easy to migrate. You don't have to change your application very much. So these are the big reasons why people who are on the MySQL family find Aurora attractive. There are people who are on commercial engines, maybe on SQL Server or Oracle or DB2. And for them, I think the attraction is different. I mean, they certainly have to go through migration. And for that, we have various migration tooling and services, the database migration service. But certainly a big part of the value proposition for these customers is the cost. They save a lot of money. And the integration of the cloud ecosystem is something that we do in a very big way. It's a big differentiator. And in terms of performance and availability, in fact, in terms of availability, I think we are certainly offering more than what many commercial database systems do. And in terms of performance and throughput, we're right up there with everyone else. So these are the two, if you look at the people who are in Aurora, they are either people who are coming in from MySQL family of engines, or those who are coming in from commercial engines. We are actually starting to see over the last 2 to 3 months some number of people who are coming in from various NoSQL systems. Maybe too early to say that it's a big wave, but it's certainly something that we're seeing and monitoring. I'm going to talk about a lot of our recent announcements in more detail for the rest of the talk, but they go along this gamut of performance and availability, ecosystem integration, reduction of cost. One of the big pieces of feedback we got from day one when we launched Aurora was people wanted it on smaller instance sizes, and we've now announced Aurora support on T2.small. You can run Aurora for $1 a day. And we are also now on on many different regions. We've launched in London, in Montreal, in Cleveland, in San Francisco. We're available in all 3 AZ regions. That is, most AWS regions have at least 3 availability zones, and in all of these regions, Aurora is available. There are a few that only have 2 AZs, and Aurora is not available there. In terms of MySQL compatibility, Aurora is compatible with MySQL 5.6 and with InnoDB. By and large, application compatibility has not been a problem for our customers. In terms of 5.7, it's a major effort for us. It's a big commitment. We would love to be able to delight customers, from MySQL, but we want to make sure people understand that their MySQL investment is still useful. We are working on 5.7 compatibility. It has taken us a little longer than we expected, but we hope to make it available in the next few months. Until then, we have backported over 81 fixes from various different MySQL releases, and we continue to do that as people hit issues that they need a critical fix for. So now let's look into performance, and I'll start by talking about designing for performance first. So we've talked about before, earlier in the slide, I bragged about 5x performance throughput advantages. So it's certainly something that's a big part of the Aurora value proposition. So let me talk about philosophically how we think about performance. At a high level, 50,000-foot view, fairly simple. We say, you can figure out how to do less work and how to be more efficient at doing that work. You're probably in good shape. So let's think about doing less work first. Databases, certainly, people in this room know very well, database is all about I/O. It's our view that in a cloud environment with kind of the failures you'll see at our scale, it's very important to decouple storage from the network. And once you're going to this world that your storage is attached to the network, when you think about I/Os, the big burden that I/Os now have on your infrastructure is really on the network. It's all about the packets per second you can sustain. So I would say that while storage and compute capacity have evolved over the years, the network capacity has not kept up. So from our perspective, anything that you can do to reduce IOs is going to reduce the impact on the network, and it's going to fundamentally transform your performance, your throughput profile. So big part of the emphasis in Aurora, when you talk about the do less work column, is all about fewer IOs. Other aspects of it also exist. If you can offload work from the database engine, that's goodness. We took backup and recovery, which steals compute from the database engine. We moved it out to the storage service. We took recovery, which is a very painful aspect of what happens in the database engine, and we moved it out to the storage service. We rebuilt the MySQL query cache. And so if you can cache prior results in an effective way, in a scalable way, that is very good for the application. But in general, when you think about doing less work, the big impact comes from reducing I/O. In terms of the other side of the column, how can you be more efficient at doing what you can? Big insight for us is that high throughput processing is all about reducing context switches. If you can figure out a way to avoid context switches, you can get much better throughput. And for us, it's all about processing data as asynchronously as possible, moving things from the foreground latency path to the background latency path, and other things that we do, batching, using lock-free and latch-free data structures in our implementation. So there's very many things we do under the covers, and I'll talk about some of them in this presentation. So if you remember the first part when I talked about the scale-out architecture, I mentioned an important aspect of the Aurora design, that we don't write full pages anymore from the database engine to the storage service, and instead we write only log records. And by log records, I mean the deltas, the diffs, the redo log records. So fundamentally, by writing only redo log records and not writing full pages, you can reduce drastically the amount of IOs that you're generating from the database engine to the storage service. So that's a big part of the do fewer IOs aspect. So let's look at this in an example and see how this all breaks down. I'm going to start with thinking about regular MySQL. Let's say in the RDS MySQL environment, where you can use, anyone can set this up on their own. We just used RDS MySQL because it does such an amazing job at setting up and managing this kind of a mirrored MySQL environment. So in this world, you have your primary instance running in one AZ and a secondary instance, a standby, in another availability zone. The primary instance is writing to EBS, Amazon Elastic Block Store. And that data that's being written to EBS is being mirrored within the same region. Now, using synchronized mirroring technology, we also replicate the data written to your local EBS to the standby EBS volume in the other AZ, where it is also then written to a local mirror. Now, there's a lot of writes going on here. And in fact, if you look at what is being written, it's actually quite a bit. The green arrows reflect the actual transaction log, your redo log. The yellow arrows reflect the bin log. We write the bin logs also to S3 for point-in-time restores. Most people end up having a configuration something like this. Then there's the actual data, and you have to write your dirty pages to disk, and you have to write them at some point of time. You write them on cache eviction, you write them on checkpointing, you have a background writer that writes it. And then, of course, you have your double write buffer that you'd employ in InnoDB to avoid torn pages and partial writes. And then there's your metadata, your FRM file. So all of this data is being written. So first, a lot of data being written, but more importantly, if you think about the flow of operations, steps 1, 3, and 4 are sequential and synchronous. This means that you have increased latency and increased jitter. So let's talk about each of these for a second. Increased latency is because the latency is additive. You do 1, and then you do 1 and 2, then you do 3, and then you do 4 and 5, and your total latency is the latency of all of these. But there's also jitter because you are in this world at the victim of the slowest step. In a cloud environment, at scale, any one of these operations may perform slightly slowly. And if that happens, your overall operation ends up being slowed down. from a distributed systems point of view, you can think of this architecture as writing to a 4 out of 4 quorum. You have to make all your 4 writes work before you can move ahead. So because you're writing so much data, and because of this synchronous model of writing data, you have high latency, and you have high jitter. And in fact, if you look at running, we ran a run of sysbench write only over 30 minutes. You could sustain 780,000 transactions in that 30-minute period, and averaged about 7.4 IOs per transaction. So let's look at the counterfactual world. What if I had something similar running with Aurora? So with Amazon Aurora in this similar environment, what we have is the database engine writing out one writer node writing out to the storage service. The 4 out of so we do our writes on a quorum-based model. So I mentioned earlier that pages are replicated 6 ways. While we send each write to all 6 copies, we don't wait for all 6 copies to succeed. It's enough if 4 out of the 6 copies succeed. That's the 4 out of 6 quorum that we're referring to here. And by only having to wait for 4 out of the 6 writes to succeed, you've eliminated or reduced the impact of outlier performance. Now, if you look at what actually is being written, it's only the redo log records, only the green arrows. Now, we also send the metadata from the primary instance to the replica instances, but it's a dramatically smaller amount of I/O that you're actually writing on the network. So what happens is, as you have your concurrent transactions operating on the master, you batch together the redo log records of various transactions happening at the same time. You batch them together based not on the time at which they occurred or the order in which these log records were generated, but based on the target partition of the overall volume that each log record needs to go to. So you batch together log records headed to the same physical storage nodes, and you send them to the storage nodes. So if you think about what's happening here, first we only write redo log records. This can all happen asynchronously. We eliminate full page writes. So all the code paths that you normally write dirty pages in, dirty page writer in the background, checkpointing, cache eviction, we just kill all those code paths. They're all cauterized. And so if you think about it, because we take each redo log record and we write it 6 ways, there's actually 6x more log writes. But overall, it turns out that we do about almost an order of magnitude less of traffic on the network. So because of the quorum model I talked about, we have a lot of tolerance to outlier latency. If we can't reach one particular node for a short period of time, that's actually okay. You can still make progress. So when you run the same kind of experiment I talked about in the previous slide, a 30-minute sysbench run, you can actually sustain about 35 times more transactions. And it turns out that you only run about 0.9 IOs per transaction. So, pretty dramatic improvement in what I talked about earlier, just less IOs. And because of this model of doing things asynchronously and being tolerant of outliers, you've reduced latency and you've reduced jitter. So, yes, I have a question here. So the question was about batching together writes and if there's any potential for data loss. So there is no data loss because of the commit model, and I will talk about that a little bit later. But at a high order bit, there is a protocol similar to the write-ahead log protocol that you'd have in a normal database engine, where you would only commit a transaction after the individual log records of that transaction have been hardened, have been written to at least 4 out of the 6 nodes. So long as you are able to maintain your quorum, you're able to write to 4 out of 6 nodes successfully, you can guarantee that you won't lose data as long as you've not lost at least 3 nodes in your quorum group. So if you dig down into I/O traffic in the storage nodes, I talked about the I/O traffic between the database engine and the storage service, and now we look into what happens actually inside the storage nodes. There's a lot of things going on in this picture, but you can think about writes and reads interacting with the storage nodes. Writes are basically the stream of log records, and the reads are requests for individual pages. So when a log record comes in, we do the very minimal amount of work to durably write that log record and then send the acknowledgement. That piece of work, the minimal amount of work to do the durable write, is all that is in the foreground latency path. Everything else happens in the background. And there are things that happen in the background. We will take that log record, we will organize it closer to the page it refers to. We will keep track of, when a given storage node is responsible for a collection of pages, we'll keep track of the sets of log records that are destined for that particular group of pages and see if we've got all of them. If we have holes, storage nodes will gossip with other storage nodes in their group to say, hey, I seem to have missed log records between 20 to 25. Do you have them? Can you give them to me? So storage nodes work to automatically repair missing history. And we will also do in the background coalescing of the log records. Now, if you take a page and you take a log record, you can apply a function called a log applicator to get the new version of the page from the old version of the page. And so we, continuously in the background keep running this log applicator, and this is the scrubbing process that we talk about here to get new versions of the pages. And so you do that in the background so that when a read comes in for a page, you have hopefully already applied the redo log for that page, and you have the right version of the page that you can actually hand back. In case the read comes in too soon, we will coalesce the log records on the fly, but in the general case, that happens rarely. So if you think about this overall architecture, we've taken a whole bunch of operations that are in the foreground path, we've moved them to the background path, and various kinds of things that happen normally at recovery, for instance, or backup, they're now happening in a way in this highly parallel, highly distributed fashion, where you can reason about capacity and utilization at the fleet level and not at the level of an individual instance. So it's not like every database engine that's connected to a given storage volume is active at the same time. So you actually do have background cycles to do this continuous redo processing. And so by doing this redo processing independently, you can reduce the impact of, for instance, recovery. So now let me talk about Aurora Replicas, because in earlier slides I had diagrams that had a replica instance and a writer instance. Aurora replication is a little different from MySQL replication, which is logical and based on bin logs, where you have a replica instance that has its own independent volume. You'll have extra storage calls for each replica instance, and where the replica is applying your bin logs. So in the traditional model, this happens logically. You're shipping SQL statements to replicas where they're being applied, and you're going to have a write workload that's roughly similar on both your writer and your reader, your replica instance. And so, over time, many of our customers have talked about in the traditional MySQL context, you can have, for instance, drift. The drift can be, even of the order of minutes between the master and the replica. Aurora replication is very different. So first, the master, the writer, and all the Aurora replicas are mounted on the same shared volume. So you're not writing data twice. If you could have up to 15 replicas, and they're all using the same underlying storage volume. Next is we do ship log records from the master to each replica, but what we're shipping is a physical log record, the redo log record, it's not logical replication. When a log record reaches the replica, we look to see if the log record refers to a page in the buffer cache of the replica. If it does, we actually apply that log record and modify the buffer cache in place. So we do this using the same log applicator function I talked about earlier. If the log record applies to a page that's not in the buffer cache, though, we don't care, we just discard it. Either way, whether it applies to a page in the cache or not in the cache, we don't generate writes to storage in the replicas. So it's fundamentally very different from what's going on in traditional MySQL. And so you have much more available capacity for new reads in the system. And also, as a result, you will see much less lag in practice, and I'll talk about that in a second. One more thing I should mention is the transaction isolation model in the replicas. In the replicas, you get repeatable read isolation. In fact, you get a version of snapshot isolation. You get to advance the read views to get your transaction snapshots as commits are seen. So commits are happening in your master. They are not synchronously waiting for the log records to reach the replica. But as the commits happen in the master, the information about transaction commits is being relayed to the replica. And that is what is used to advance the read view or the snapshot in the replica. No, if you're really constrained on, the question was if you're running the same underlying storage, will replicas help in scaling the writes, I guess is the question. The replicas will help in scaling the reads because there are, if you remember, each copy is replicated in multiple different nodes. So there are many different places to get a copy of the page. Right. So the reads that are coming in the replica are happening independent of the writes that are happening in the master. And if the reads refer to pages in the cache, they get served from the cache. If the reads refer to pages that are not in the cache, we go get it from the storage volume.
But you can't, how can you say that for certain? If there are 6 copies, you can't tell which one. The master is writing to all 6.
Right.
The replicas are reading from all 6.
That's right.
It's not like the master is writing to 2 and the replicas are reading from the other.
Right. So, if your concern is about capacity, that's something that we are managing, like I said, at a fleet-wide basis, right? We have the network capacity, certainly, and it's a matter of adjusting the, what is available on each of the different nodes. If you notice, we reduce the likelihood of going, to the storage volume because we are actually applying the log records in the cache itself. So it's not like every read that's coming to the replica is going to the storage volume. Many of them are going to be, serviced by the cache itself, by the buffer cache, and it is a function of the working set. So in practice, we don't see the concern that you're talking about, by and large. So if you look at replica latency that customers experience. So one of our customers talked about in their workload prior to migrating their workload to Aurora, they saw replica lag of almost, that could go all the way up to 12 minutes. With Aurora, although they had 4 replicas, the lag that they observed never exceeded 20 milliseconds. So that was, a pretty good data point. Now, we have many customers with who are having replica configurations. We generally see these kinds of numbers, 20 millisecond lag across the fleet. So this is something that's become a big part of how Aurora customers use replicas, Aurora replicas. They do actually use the replicas for scaling reads, perhaps more than they would have done in their prior environment. So the next piece, I want to talk about 3 things that we did in Aurora. One of them is about how we have asynchronous group commits, and the other is about how we implement a different thread pool, and third is about the lock manager. So because these are 3 fairly important things that were part of Aurora. So first, let's talk about the commit model, and I think there was a question about this earlier. So in the traditional database engine, redo log records are being generated as the transactions are performing writes. And these redo log records are put together in write-ahead log buffers where they're flushed to disk on transaction commit. So if a thread is servicing a transaction and it receives a commit message, that thread cannot acknowledge that commit until the log records have actually been written to disk. In Aurora, we have a slightly different protocol that's similar in intent. The intent of the write-ahead log protocol is you can only acknowledge a transaction if the underlying log records have been durably persisted. In our world, we say until the log records have been hardened. And a log record is hardened when it has satisfied the quorum property. It has been written to at least 4 out of the 6 nodes. And so in Aurora, what happens when you have a thread that's serving a transaction commit is once the commit log record has been generated, the thread does not need to wait anymore. It can move on to do something else. And as the log record's durable point increases across the system, the durable point is the high water mark below which we can guarantee that all log records have been hardened, have satisfied the quorum properties. As the durable point increases, we are able to asynchronously say, look at all outstanding transactions that are waiting on commit and go and acknowledge them. So it's it's a fairly nitty-gritty detail I talked about, but what it does do is let you have, use your threads better, and doesn't let you have unnecessarily threads waiting around just on transaction commit. So it's a fairly big part of the performance story. The next part is the thread pool. So there are different kinds of thread pools that are available with MySQL, with different versions of MySQL. What we've built is an adaptive thread pool where connections are reentrant and multiplexed to different active threads. We dynamically size the thread pool, and as a net, we can quite easily handle many thousands of concurrent connections at the same time. And finally, the lock manager. The MySQL lock manager by default has a single global mutex that is guarding access to the entire lock manager. We completely rewrote it, and so while we offer the same locking semantics as MySQL, we don't have a single global mutex. We built the lock manager using a latch-free implementation or a lock-free implementation. So you have concurrent access to the different lock chains. And we also have latch-free deadlock detection. As a result, it's also a big part of the throughput story. So I would say, I alluded earlier on that a big part of performance was fewer IOs. Once the number of IOs were reduced, we were able to attack other bottlenecks. So finally, in terms of performance, as a net result of doing all of this work, we have read and write throughput that scales with instance sizes. And so you can go up to over 100,000 writes a second on an R3.8x large in Aurora, and over 625,000 reads a second on that same R3.8x large. Some of our customers have, there's a customer that reported, web transaction response time. So this is kind of an aggregate response time. This is not a breakdown of the amount of time spent in Aurora, but they had this very clear pattern that after their Aurora migration, their response time dropped from 15 milliseconds to about 5 milliseconds. It's hard to say exactly, which part of it is ascribed to Aurora, but this is an interesting overall, end application response data point that we got.
What else changed apart from the Aurora side?
Nothing. They only changed their database. They switched from having a MySQL environment to Aurora. The instance sizes were the same, R3.4XL, and they had the Aurora environment. And
So why is it hard to tell what's attributed to Aurora?
no, I'm not saying it's hard to tell what attributed to Aurora. I just, I can't explain that 10 milliseconds. I can't break it down into, we did an individual query perform better or what throughput I have. I don't have the data. This is just an overall from an end point of view what they showed us. I would attribute the improvements to Aurora, but I can't break it down to is it on writes or reads and all of that. We've done a bunch of recent performance improvements. I'll do a quick tour through them. The first is faster index builds. MySQL 5.6 inserts entries into a new B tree when it's building a secondary index on a top-down fashion. 5.7 improved this to build the B tree bottoms up. We leveraged the 5.7 infrastructure and we made some changes to that. Have a pretty good secondary index building performance as a result of this work. In terms of hot row contention, we have some very good results with TPCC benchmarks where you have a lot of transactions updating a common row. And the way the MySQL lock manager will handle this sudden bloat in the lock chains can certainly be improved. And while the Aurora lock manager is very different, we made some big improvements here. Used a dynamic programming algorithm to get a much better performance in these kinds of hot row contention scenarios. And in fact, as a result, we have some very impressive numbers in TPCC for Aurora versus both MySQL 5.7 and 5.6. 5.7 certainly improved TPCC performance much better, but Aurora takes it to the next step. Similarly, insert performance, we cache the cursor position to avoid resetting the cursor for every individual write. And this was delivered back in December 2015. This helps across the board in DML operations. We introduced spatial indexes in December 2016. MySQL 5.7 has an R tree. We did something fairly different. We built something called a z-index, or to be precise, an XZ index. This has many different properties that make it better than an R tree for cases, for instance, when you're doing a lot of updates in OLTP workload. The externals are actually 100% compatible with what you do in MySQL 5.7. When you say create spatial index, you say the exact same command, except under the covers, we don't build an R tree, we build a Z index on the underlying B tree. And then we also had various improvements to both cached and non-cached read performance. In cached read performance, we changed the data dictionary. Instead of having a single global mutex, we improved concurrency for the dictionary catalog. We improved the scheduler, and we also built a new read view implementation for snapshot isolation. For non-cached read performance, we did a few things that are important. Some of them, for instance, is we try to be smart when we are trying to go after a page. You can go after a page in any one of the 6 copies. We improved how we try to use recent history to decide which page to go after. We also implemented something called logical read ahead, where we actually try to read prefetch pages into the buffer cache based on the access patterns in the B tree. We added high performance auditing. We started with the MariaDB server audit plugin, but if you use the server audit plugin by itself, you'll get, it'll impact performance a lot. When you're running 600,000 reads a second, and once you turn on audit, if you can only sustain about 50,000 reads a second, that's pretty embarrassing. So we, did a, fairly significant change in how we, built it using the same user experience, but very different implementation. We can sustain, up to 500,000 reads a second now with auditing on. So that's, a big feature we announced a few months back. We introduced something called fast DDL that lets you do schema migrations. Right now, fast DDL, it's actually now publicly available. Right now, fast DDL only works for adding a nullable column in the end of the, in the end of the row. But we plan to, support many other operations. The way fast DDL works is we keep track of the schema history in some extra metadata, and we acknowledge the DDL command immediately, but we lazily, using a modify on write primitive, upgrade individual pages as they are being written into. So this is the fast DDL. We have a pretty aggressive roadmap for fast DDL. We want to support other add column operations very soon in the next coming months. But then we also want to do things like reordering columns for things like modifying the data type of columns, various other kinds of things that we want to do here with schema evolution, because we certainly hear that as a major pain point in the MySQL community. Finally, I'm going to breeze through the availability section. I spent a lot of time on performance. In terms of availability, the high order goal is to survive catastrophic failures. So there are 6 copies of each page across 3 availability zones. In terms of read availability, in terms of read and write availability, we can lose a complete AZ and still be able to read and write data. But we want to be able to lose a complete AZ and lose one more node and still not be able to lose data. So we have a 4 out of 6 write quorum. The read quorum is 3 out of 6. Now, I want to be very clear, we don't do quorum reads on a normal read basis. We have state in the database engine that tells us where we can go and read data. But the read quorum comes into play on recovery. So we know, where, how to safely rebuild the database engine, the volume after a crash. Storage volumes today grow up to 64 terabytes. We are considering how to increase that, as people are asking for bigger volumes. We do continuous backups to S3 because we are writing redo log records to the different storage nodes. From the storage nodes, we continuously keep writing the redo log records and the pages to S3. We continuously monitor nodes and disks, and if they are bad, we repair them. If we do heat management, if there's more load on one particular storage node or disk, we will move segments of that particular storage node, and all of this happens seamlessly, and customers don't see any of this. We have continuous backups that happen automatically. You can take name snapshots. You can do point-in-time restore. Crash recovery is a huge advance in Aurora. You can be running 100,000 writes a second. You can crash, and you'll be back up in about 10 seconds. And the reason is because we don't have to do redo recovery. And the reason we don't have to do redo recovery on restart is because we are effectively doing this all the time. So we've taken something which is a highly time-consuming operation. The worst possible time can happen is when your database is down. We take something which is very painful in the worst possible time and amortize it over the life of the database. So instant crash recovery is a major value proposition of Aurora. We made the buffer cache survivable. It moved it to shared memory. So after a crash and you start up, your buffer cache is actually still warm. The read replicas you can promote from a writer to a read replica. You can manually promote it, but if there's a failure, if there's a node or a network event that means you can't reach the writer, the service will automatically promote one of the read replicas and make them the new writer. And so you get much faster failover. We worked with the people in MariaDB, and they have a version of the MariaDB Java driver, the JDBC driver, which can even improve the time for DNS propagation. Instead of waiting for full DNS propagation, you can get even faster failover by using the MariaDB driver. And anyone can do this, can build a similar binding for any programming language. If you've done it, we'd love to hear about it. I know I'm running out of time, so I'm going to quickly talk about a few more things that we've done recently about availability. One thing is about zero downtime patching. So when you patch a database, it's intrusive because all the database connections go down because you've replaced you have a new version of the database engine. One of the things we've just launched is something called zero downtime patching, where we spool the state, the application state of the database. We look for a safe point when there's no active transaction. It turns out you could even be running a sysbench write-only workload, and you can still find a safe point where there's no active transaction. It doesn't have to be long, it just has to be microseconds. And then we patch the database engine. We put the new binaries on the instance. We call exec and rebuild the daemon. And then from the spooled state where we've parked the connections, we can build the connections back up, and the database is open for business. And the client connections are none the wiser. They've just seen a blip, but the connections haven't died. So this is something that we're very excited about. It's really cool. There are still several constraints for zero downtime patching, but we're working to improve them. We are going to release database cloning using a copy on write technology. It'll be out hopefully next month, where you can create a clone of a database, even a terabyte size volume, almost instantly. As these two databases, the two clones diverge, as they cleave, we will make copies of individual pages. And so one other advantage of this is if things don't change very much, you're not actually paying for both clones. You're only paying for the new pages that are being created. So this is something that's very exciting. I think it's very useful when you have test environments. You want to take your production environment and move to a test environment. And finally, database backtrack. It's also planned for second quarter, where you'll be able to, let's say we had, I don't know if people have seen the XKCD comic about little Bobby tables. The fat-fingered move where you go and delete a whole bunch of rows. You can do an instant backtrack to some amount of time in the past. And you can go in the past, you can go forward. This is also something that we get because of the whole new abstraction of log records that we've built. So this is also coming in Q2. So I'm pretty much at the end of my content. There are a few other blockers that we are constantly removing, various certifications that we have, HIPAA compliance, for instance. I talked already about Aurora for T2 medium and T2 small. And so we can run it really cheaply now for dev test environments. There is a near-term roadmap of what we're doing. Primarily trying to make it easier to migrate new applications to Aurora, but we also have various other strategic items. So I'm sorry for buzzing through the last 10 minutes really fast, but I'm happy to chat about anything in more detail. Yes, question?
Question about the cost region. We were talking about those cells that fall in one region. What about the cost region? I know that we're using MySQL for that, but dealing with that is not good.
That's correct. It's a good question. The question was about cross-region high availability, particularly for business continuity. We do have today managed cross-region replication that uses binlog replication, and we all love binlog, but it has its challenges. We are working on physical cross-region replication. I don't have an ETA for that yet. Oh, that's a good question. So the question was not just because with audit you can log not just the query but also the contents. Right. Okay. I was points taken. I'll go take a look at this question. We do have something like this under the covers. We are not impacted by EBS very much. We are only impacted by EBS on the small instances, the T2 small and T2 large, because the other instances don't use EBS as such. We do have this. We avoid taking circular dependencies in AWS in general. But yes, we have contingency plans for all of these things. I don't know about that. I can find out and I can take your contact information and try to get an answer. Yes, question.
Is there a particular reason why performance schema is not enabled by
Yes, I think in Aurora was at 5.6.10 when we released it, and I think there were a lot of bugs that got fixed between 5.6.10 and 5.6.30. So I think we disabled it primarily out of an abundance of caution. And now we've backported. Some of those 81 fixes are actually the performance schema. We still don't turn it on by default. We certainly don't turn it on the small instances, but it's something we can consider. It's just inertia.
Yeah, that would be very helpful. And a follow-up question for that. All the metrics monitoring available from the cloud, right? So
We absolutely do. There is enhanced monitoring, which is basically gives you more fine-grained monitoring. But we also talked about Performance Insights, which is a new service that we're offering. It is being launched with Aurora on Postgres next month, but we also are going to bring it into Aurora on MySQL. You're talking about upgrading instances or versions? Like, are you saying 5.6 to 5.7? Right, so even minor updates, we are starting to have catalog changes. So the way it works is, when you are upgrading it, we apply the catalog change, and then we upgrade the database engine. We apply it as part of the upgrade process. So right when you have started, but before you accept new connections, we apply the catalog change, upgrade the catalog right then and there. No, at this point we don't have a way to go back. It is something that people have been talking to us, and we have taken that feedback fairly seriously. So we don't today have a way to go back.
So for the performance benchmark, how many redirectors do we set up in the
So there's different benchmarks. We have run benchmarks with multiple read replicas. The big 5x that we showed, actually that run does not have any read replicas. But we can run 100,000 writes a second with read replicas. It depends really on what kind of workload you're running and which instance type.
Yeah, so the follow-up is because we can support up to 15 read replicas.
Correct. Correct. There will be an impact for sure. If you have 15 read replicas, we probably won't sustain 100,000 writes a second. Definitely. Yes.
Do you plan to add the ability to add schema privilege in Aurora as well? Because that was a missing part in any RDS. So RDS doesn't support.
Yeah, I don't believe we plan to do that. I think at this point our security model is fairly similar to RDS MySQL. I'd like to hear why though. Maybe we can take it offline. Okay, I'm getting waved down, so I should we can take this afterwards. All right, thank you very much.